Section 4.6, Modeling with Exponential Functions, Part 3. Newton's Law of Cooling. Here's what Newton's Law of Cooling looks like. What we want to do first is go through and make sure we understand all the variables involved. Once we understand all the variables that are involved, we can then easily match up problem information with those variables. D sub 0 is the initial temperature difference, between an object and its surrounding. Ts is the surrounding temperature. So here we have D sub 0, here we have Ts, two of the variables from the formula. Okay, so D sub 0 is the initial temperature difference between an object and its surrounding, and if its surroundings have temperature Ts, then the temperature of the object, and that's what Newton's law of cooling represents, the temperature of the object at time t, is modeled by the following. K is a positive constant that depends, or the K is the positive constant that changes with different types of objects. Okay, so with that in mind, let's look at problem 27. A roasted turkey is taken from an oven when its temperature has reached 185 degrees Fahrenheit and is placed on a table in a room where the temperature is 75 degrees Fahrenheit. If the temperature of the turkey is 150 degrees after half of an hour, what is the temperature after 45 minutes? Lots of information, but if we keep track of what our variables represent, maybe it's not so bad. Okay, a roasted turkey is taken from an oven when the turkey temperature is 185 and placed into a room that is 75 degrees Fahrenheit. So there's our object, the turkey, and there's the surrounding temperature of the room, 75. And so what D sub 0 represented was the difference between the object, 185, and the surrounding temperature, which was 75. So what we know about D sub 0 is that's 110. Ts is just the surrounding temperature. That would be the temperature of the room. So that's going to be 75. Okay, then we have time t. We got to figure out t, and we got to figure out k. All we know are these first two variables, Ts and D sub 0. Okay, so let's continue reading. If the temperature of the turkey is 150 degrees after half an hour, and we're going to stop there because that's going to be how we find K, our constant. 30 minutes is a half an hour. We want our time units to match, so we use 30 instead of half an hour. 30 minutes is a half hour. Okay, so the temperature is 150 after 30 minutes. Okay, so T is our temperature, 150 after 30 minutes. So when we do that e to the negative k, time is 30 minutes, so we can fill that in. T of S was our surrounding temperature. We said that was 75, and D sub 0 was the difference between the object and the temperature. We said that was 110. Here's what we're going to use to solve for K. We subtract 75 first. So if I subtract 75 and I subtract 75 over here, we get 75 is equal to 110 e to the negative 30k. To move the 110, since this is a multiply, we're going to go ahead and divide. So we have 75 divided by 110 is equal to e to the negative 30k. How to get rid of e? Since it's an exponential, a log undoes an exponential. So we're going to ln both sides. So we have the ln of 75 over 110 is equal to, ln e is going to cancel out, so we just have negative 30k. Dividing both sides by negative 30 and there's our K for our object, which is the turkey. Okay, so let's get this put into our calculator so we can figure out what K is. All right. We are going to take the natural log of 75 divided by 110. That's going to be divided by negative 30. And so K is approximately 0.0128. 0.0128. Now we have a model for our turkey in terms of Newton's law of cooling. Okay, so let's look at our model. We have T sub T is equal to Ts, we said that was 75, plus D sub 0, we said that was 110, e to the negative, we just found K, 0.0128 T. Okay, for part A, now we want to know what is the temperature after 45 minutes. So we have T of 45 is equal to 75 plus 110 e to the negative 0.018 times 45. Okay, 75 plus 110 times e raised to the negative. Now here, the earlier you round, the further off your answers are in the end. So if I don't want to type all this in some calculators you hit second enter, that takes you to ANS, last answer displayed. In some calculators you can just highlight and hit enter and it will bring it in where you need it. Okay, so times 45. And so after 45 minutes, our turkey temperature is 136.9. And that would be degrees Fahrenheit. Okay, after how many hours will the turkey cool to 100 degrees Fahrenheit? Okay, so what I did was I already highlighted our equation. I'm going to hit copy. I'm going to get a new page. And then we're going to do a quick paste. We want to know how long it's going to take for our temperature to reach 100 degrees. Okay, so that's our temperature, 100 degrees. We have 75 plus 110 e to the negative 0.128. And we want to know, I need a 0 in there, we want to know at what time we're going to be at that 100 degrees. Okay, so if we solve, we're going to subtract that 75 first. So that's going to give us 25 is equal to 110 e to the negative 0.0128 t. To move that 110 over, we're going to do a quick division. So we got 125 over 110 equals e to the negative 0.0128 t. How do we get rid of e? ln both sides. When we ln e, that's going to cancel that out, leaving us with negative 0.0128 t. Now all we have to do is divide that over. Okay, so let's see what we get for t. We're going to plug that into our calculator. Okay, so we have the natural log of 25 divided by 110. That gets divided by a negative. Now we need that 0, 1, 2, 8. So I'm going to bring up and highlight, bring that down. Once we hit enter, so how many minutes, because we're solving for time, how many minutes is it going to take for the temperature to become 100 degrees, 116.1 minutes.